All right, hey you guys. So we are going to finish your AP test cheat sheet this week. We're also going to kind of talk about some more information I got about your AP test. So for your AP test, you guys should have gotten an email from the AP board to your personal emails. Please make sure you read all of those. They have information about how you're going to log in, what website you're going to go to, kind of policies, procedures, things like that. I have been told that somehow they're going to monitor kind of what tabs you have open while you are taking the test. It is Open Note and Open Book. Sorry, I couldn't think of the word. Open Note and Open Book. But it's not like a collaborative test. So you are not allowed to work on it together. So I have been told that if you guys go and try and Google the exact question, or if you open like a Reddit link or tab or forum or something like that where people are talking about the question, it'll somehow know that and then close your test, tell them you were cheating, and then give you a 0. So you just want to be aware of that. So you can't cheat that way. You know? So you're going to have to be creative with how you use your open notes, you know? Okay, cool. So glad we talked about that. It is not optional. Mrs. Harrison, who is our one of our assistant principals in charge of like what classes you get to take, in charge of counseling and stuff, has said that if you are a junior, sophomore, or freshman and you do not take your AP tests, they will not put you in AP classes next year. So if you're like, hey, well, they said it's optional in the email, so I'm going to just pretend I think it's optional and then not take it. Just because you don't want to take it, then you're not going to have AP classes ever again. So good luck with that. So just be aware. Seniors, there was a consequence for you guys. I don't remember what it was, though. I'll double check and I'll get back with you. So be aware. Actions have consequences or something like that. All right, so let's look at our AP test breakdown. So last video, we went over a couple things. We went over forces, we went over energy and momentum. So let's just kind of look at those things really quick, go over them. They're really where we want to focus most of our energy because because do you see these big numbers here for the percentage of how much the test is going to be on that thing? They're where most of the stuff is. So we really need to know that stuff pretty well. Kinematics and torque and rotational motion, also pretty important, like as important as momentum, for sure. But way more important than, circular motion, universal gravity, or simple what? Okay. So let's review the 3 we talked about last week, or rather the 1 we talked about last week and the 2 you guys were supposed to fill out on your own. If you sent that to me by Sunday at midnight, then I put in your points for that. And if you didn't, I didn't. So there you go. Be responsible. Turn stuff in by Sunday. All right. So next sheet. All right. So here's what we talked about last week. Our dynamics, which is a fancy word. Excuse the car alarm going off. It's hard living in the hood. I didn't choose the Thug Life. Thug Life chose me. And my credit score chose Thug Life too. But anyway, dynamics are forces. So we need to know Newton's 3 laws, and we need to know what they all say, because you're going to want to name drop these bad boys on the test. You'll be like, hey, you know who said that? Newton. Okay. So the first law says the sum of forces equals 0, then A equals 0. This means sum of forces. That means if I add up all my forces, they equal 0. So they all cancel out. So if all my forces cancel out, acceleration is 0. Things don't accelerate. They're going to keep going the same direction at the same speed they always were. So forces can push on stuff and have it still do the same thing. There just has to be another force to cancel that out. All right, second law says sum of forces equals MA. So if our forces are unbalanced, then we set it equal to ma instead of equal to 0. This is just like the only equation anyone knows in physics, F equals ma. Okay. Third law, if I punch you in the face, your face punches me in the hand just as hard. This means every force has an equal and opposite applied reaction force because of it. So if I push my fist into your face, because your face is made of bones and other hard things like cartilage and fat and mucus and, you know, teeth and stuff, when my flesh ball here hits your skull ball here, okay, I can't push on you without you pushing on me, right? Like if we're touching, there's mutual push there, right? See, yeah, done. Okay, anyway, so because things are touching, they push on each other is basically what it's saying. And this law just tells us that however hard this pushes on this pushes back on this just as hard. The forces are equal. That's the important part of Newton's third law. Okay, so whenever you think you're going to use forces, right, and we'll kind of talk about why is this a good thing to use at some point, then here are kind of the steps you're going to want to do. If you go, all right, forces is my approach, I'm going to shoot this thing to death with forces, and if not, then maybe I'll use something else on this page because it's probably on this side. Okay, force diagram, that's one of these bad chickens right here. You've got to take your object, make it a little point in the middle, and then you draw all the forces that are pushing on that object. Label them. If you can't name it, you can't label it, and I'm not talking about force applied. Unless they say there is an applied force, then don't use force applied. You have to come up with a name for it. If you can't name it, don't put it on there. You've made it up. Okay, it's your object is a point. All the forces that are pushing on the object go on there. This means the object could be pushing on something else. We don't put those forces on force diagrams. These are only ones that the object feels, not forces that the object produces. Okay, 2, take all these forces and add them up. You want to pick an XY axis that makes sense for your problem. Remember we talked about like taking them and tilting them. You can tilt some axes. But regardless of how you orient them, you want a sum of forces in the x direction and you want a sum of forces in the y direction. If they're unbalanced, they'll equal ma. If they're balanced, they'll equal 0. Okay. Then step 3, read the question, try and solve for the missing variable. If you get this far, you probably got a bunch of partial credit anyway. But at this point, you might have to sub in, all right, well, they asked me what is the mass of the object. You might have to substitute weight for mg or something. What's the normal force? Well, you might have to rearrange this equation and get weight on the other side and solve for it that way, right? Something like that. So step 3 is once you've done these 2 steps, take a breath, see if you can figure out how to get the variable they're asking for at that point. Okay, here's kind of what I came up with for the other 2 important ideas that you guys were supposed to fill out last week, and then we'll go over the other 3 leftover ones today too. So energy, the first thing we want to know is the system open or closed? A closed system, not an open system. I'm just, dumb and I can't read. Closed system. A closed system are sum of energy. So all the energy in our system will be constant. Okay, that means we're not going to gain any energy and we're not going to lose energy. There's none coming in or going out. These are just the sum of the individual types of energy in the system. They can kind of bounce back and forth. Like if I have some gravitational potential energy, I could take some of this and transfer it to this, but I'm only transferring sorry, that's just my coronavirus. There's only transferring, there's no gaining or losing. So the total amount has to be constant. So that means the change in energy is going to be 0. Change in energy is also called work. Okay. we know a system is closed if there are no forces acting on the objects in the system that come from outside the system. That means if my system is like the fist, the face, and the planet Earth, then the forces on my face are the fist and weight. Those come from other objects in the system, so that would be closed. Okay. An open system means we are gaining or losing energy. Here, the change in energy or the work done is not zero. It's going to be the force that is putting energy into the system or taking energy out of the system times how far the object moves from the system while the force is pushing on it, and it has to move the same direction the force is pushing. Okay, that's what this cosine theta does. So the sum of energy changes. Outside forces are acting on the system. So we could gain energy. That would be like I have something sitting on the ground, and then someone comes around and picks it up and then puts it on a table. They just raised it up, so now there's more energy. They did work on the system. It could be I slide a hockey puck across some ice and it is slowing down and comes to a stop. That would be friction taking energy out of the system. So friction did a negative amount of work to the object. Okay, so you want to figure out, do you think it's open or closed? If you have a pretty simple, if you want to use conservation of energy, you are assuming it's a closed system. If you're using work, you're assuming it's an open system, right? Okay. So just be aware of which one you are talking about, or if they ask you a question, is the system open or closed, or how would you define the system so that it is closed? Just take these things into consideration. Well, if I want this to be a closed system, I have to include the Earth so that gravity is an internal force or something like that, right? Okay, here's all our important equations so that we have them in one spot and we kind of know what topic they go with. We have our gravitational potential energy. That's just the mass of an object times however strong gravity on the planet you're on is. Remember, on Earth, we're going to use 10 downwards. You could use 9.8 if you really want. And then H is how high above wherever we say 0 is or below the object is. So if you're lifting something or dropping something, you're probably using this. Excuse me. Let me get a drink of water. Okay. Someday I'll learn to video edit and take those out. All right. Our potential elastic energy is 1/2 kx squared. 1/2, that's just a coefficient because of calculus reasons. Don't worry about it. K is our spring constant. That's how stretchy springs are. This would be like 500 newtons per meter. That would be like a garage door or something like that, right? So it's how stretchy your spring is. Big number is stiff, hard to pull spring. Low number is bendy, flexible, easy, stretchy spring. Okay. X is how far the spring is stretched. Okay, so there you go. That's if you have stretchy springs, like you have something is pulled back, anything elastic. It could be rubber bands, it could be springs. You just want to make sure it probably follows Hooke's law, which is F equals Kx. Okay. Kinetic energy, the T is for translational. That's things going in a straight line. Okay. That's 1/2 times the mass of the object times the velocity of the object squared. So that's how fast it's going. Okay. K sub R, this is kinetic energy rotational. That's because spinning things have energy too. Just because a buzzsaw isn't moving forward doesn't mean you'd want to stick your hand in it, right? So kinetic energy rotational is 1/2 I omega squared. I is your moment of inertia. Remember, that's how hard it feels to turn something. And then omega is how fast something is spinning. So it's the rotational version of mass and the rotational version of velocity. Okay, so those are your 4 energy equations you really want to know. You are going to use those anytime you are doing calculations with energy. We also want to know that our change in energy is equal to the work. So work is change in energy. It's if I'm adding energy to the system or taking it out. The work or the change in energy is equal to the force adding energy or taking energy out of the system times the distance it moves the object in the same direction that the force is pushing. Okay, so there's the direction you're moving, there's the force, there's the angle between them. You just plug in these three numbers to the equation. Okay. So if a system is closed, try and conserve energy. Say that your initial energy, that is, let's say something starts up high, falls, and then is moving that way. You would say my initial energy is gravitational potential, mgh, equals my final energy. It fell, so it doesn't have gravitational potential anymore. Now it has kinetic translational, so equals 1/2 mv squared. And then try and solve for that. If you think you're adding energy into a system, so something's just sitting there and then it gets lifted up, or then it gets boosted or thrown or tossed or blasted, something like that. You add energy in, or something's going really fast and you stop it or slow it down or you unwind it, something like that. Then you're doing work. Try and do change in energy equals the work done, and then use this formula up here. Okay. I don't know how much power they're going to include. This is the power equation. Power, remember, is just your rate of change of energy. It's how fast you're putting energy into the system. So it's change in energy over change in time. Or I'm sure you all remember the story of my beloved friend John Power. He hates his boss. And it's because his boss always makes him work overtime. Oh, man, I miss telling that joke. All right. Last thing you guys were supposed to cover last week was momentum. So, momentum, here's all the important stuff I kind of came up with for a cheat sheet, flow charts, all that good stuff. So, again, just like energy, we want to know, do we have an open or closed system? So, for an open system, the momentum is not conserved. That is... the entire system is going faster, or the entire system is slowing down. Something like that. Yeah. Okay. Try using impulse. Impulse, the variable for impulse is J. I don't think they have that on the equation sheet. I think they just use delta P for change in momentum. The variable for momentum is P for God knows what reason. So change in momentum equals force times time. If it's an open system, try that. That would be if your momentum is changing. You want to ask yourself, are there any outside forces? Okay. For a closed system, this is if we're conserving momentum. Momentum is conserved. So you would use a conservation equation, which will look like this for your starting point. So your initial momentum equals your final momentum. If you plug in variables or equations, it'll typically turn out something like this. So momentum of the first object at the beginning plus the momentum of the second object at the beginning equals the momentum of the first object at the end plus the momentum of the second object at the end, and so on, right? It's same thing if you have like three. We'll talk about this in a sec. Okay. There are two types of collisions you need to know about for momentum. There are perfectly elastic collisions and inelastic collisions. Perfectly elastic collisions are an impact that's going to be absorbed by like a spring or something bending or flexing or deforming. This would be like two carts run into each other, but there's a spring in between them. This would be you drop something heavy in your truck bed and it bounces because the shocks in your truck bed are big springs. Things like that. So anytime you have rubbery, bouncy things, probably an elastic collision. For elastic collisions, you get two important pieces of information. Momentum and kinetic energy are conserved. You get two of them. So you get, whoops, my pen doesn't want to write. Pi equals Pf and EI equals EF. Okay, so that's perfectly elastic collisions. Inelastic collisions, These are the fun ones. These are like things blasting apart or things running into each other and sticking together. These ones do not see how not's big and like different font, and it's purple. I don't know if you can tell. I should probably get a better camera for this. Kinetic energy is not conserved. Only momentum is. Usually your momentum equation, you do want to do conservation of momentum like this, pi equals p final, but usually it'll simplify like this when you plug stuff in. Your momentum of the first object plus your momentum of the second object equals the mass of the two objects added together times a single final velocity. This is because these two objects stick together, and since they're moving together, they have the same final velocity. So we just factor the velocity out and then stick the m's together. You can take this and flip it around. So stick the m's together over here and have the two separate ones over here. That'd be, they're stuck together at the beginning and then they blast apart into two different pieces. That two different pieces will end up over here. So, there we go. All right, so if you're totally stuck with a momentum problem, here's kind of like what you should ask yourself. Are there external forces? Try and figure that out. If you think there are external forces, it's an open system, and then you should go do impulse. Force times time equals change in momentum. So you need to figure out change in momentum, and you need to figure out your force and your time. Okay, that's probably where you want to go with that. External forces. I don't think there are any external forces, right? It's just two things running into each other, and those are the only forces. They're in space, in a vacuum. They're perfect spheres, you know, the whole thing. That's a closed system, and for closed systems, you're just going to use conservation momentum. So you want to try and set up an equation like this, where you have the momentums of however many objects you have at the beginning added together, plus the momentums of all your objects at the end add together, and then these two things should be equal. Okay. If you said, I don't know, either you have no idea how forces work, or they don't give you enough information in the problem, which is maybe true. So maybe the question is it open or closed, right? That's what we're trying to figure out. I don't know. How do I tell if it's open or closed? You want to go find your initial and your final momentums and try and compare them. If you can solve for those and compare them, then a lot of times you can figure out is it open or closed, and that'll give you a hint on how to go from there. Okay, so so that this isn't an hour-long video, I'm going to cut it here and I'll upload a second one going over the second sheet. I just wanted to make sure we covered this so that we're all kind of on the same page of what's important. So, you know, see you in the next video. We'll go over kinematics, we'll go over torque and circles, which is circular motion, and then the universal law of gravity and simple harmonic motion. Cool. Stay frosty, gamers.